and welcome to a new edition of Nomadic Labs Research Seminar. My name is Richard Bonichon. I'll be chairing today's session. We are very happy to have Hakjoo Oh from Korea University with us today to talk about MicSE, an automated verification tool for Michelson programs. Hakjoo is an associate professor from Korea University, as I said, and has a pretty impressive track record of publishing in the very best conferences in programming languages, software engineering, and security. This is highly relevant here, for it means that his publications are usually backed by extended experimental results and, as we will see, tools. So thank you, Hakjoo, for making the time to be with us today. The project that he led that resulted in the MicSE tool ended at the end of last year, so this is fairly new. It was sponsored by a grant from the Tezos Foundation for verification and testing infrastructure for Tezos contracts. Before we start, here's a useful reminder regarding questions. In order for me to see them, please ask them in a stage chat. So there's a tab called chat and not in the Q&A tab. Do not hesitate to post them during the talk, even though they'll be answered at the end. So without further ado, let's begin this seminar and watch Hakjoo's recorded talk. See you after it for the Q&A session.
Today, I'm going to talk about our recent project called MicSE, which is about automatic verification and testing of Tezos smart contracts. So let me first briefly introduce my research area and research group at Korea University. I'm working on programming languages, software engineering, and software security. And more specifically, we are working on various research topics such as in program analysis, program testing, software testing, program synthesis, and program repair. And you can find more information about our research and publications at our website. So briefly speaking, the final goal of our research is to develop techniques for automatic detection and repair of bugs. So we would like to develop a tool like this, which takes a buggy program and produces as output a correct program. And to do so, we develop two kinds of techniques. First, automatic bug detection techniques take a buggy program as input and detects bugs in the code, in the program. And second, automatic repair techniques take the program and the bugs detected by the bug detectors, and its goal is to automatically generate patches for the bugs. And in both techniques, we use program analysis as key enabling technology. And the focus of this talk is on the first phase, automatic bug detection or verification. And in particular, I'll introduce the MicSE project for bug detection of Tezos smart contracts. This talk is organized as follows. First, I'll overview MicSE, what it is, and how to use it, and so on. And then I'll explain the techniques behind MicSE. And conclude this talk with some empirical results. So the goal of the MicSE project is to build a tool called MicSE, Michelson Symbolic Verifier, for verifying and testing smart contracts in the Tezos blockchain. And this figure below depicts the overall workflow of MicSE, which consists of two key components: property prover and property refuter. So in overall, the MicSE tool takes two inputs. First, a smart contract written in the Michelson language, and second, a safety property to verify. And typically, the safety property is annotated as a comment in the source code of the smart contract in the Michelson language. So given a smart contract and a safety property, two inputs, the goal of the prover is to formally prove that the smart contract satisfies the given property for all possible executions. And the output of the prover is either proved or failed. When the output is proved, it is guaranteed that the given safety property will never be violated at runtime of the smart contract. And when it fails to do so, we may have two possibilities. First, safety property, it is impossible to prove the safety property because the property is actually not true, which means that the contract has a bug. And second case is that the prover can fail due to the inherent incompleteness of program analysis techniques. Any program analysis technique cannot be complete. So the prover cannot precisely differentiate these two cases. And this is why we need the property refuter in the next step. So when the prover fails to prove the safety property, the refuter attempts to refute the safety property. The outcome of the refuter is either refuted or failed. And when refuted, the contract is proven to be buggy, and the detected bug with a concrete error trace that demonstrates the bug will be generated. And when the refuter fails, there are again two possibilities. The contract is buggy, but the refuter cannot prove it due to the incompleteness of its algorithm. And second case is that the contract is actually safe. And in this case, again, MicSE cannot prove or disprove the safety of the given contract. So we have implemented MicSE in about 16 kilolines of code, of camel code, and it's open source. So if you are interested, you can find the source code and some data, including benchmarks, from this GitHub repository. So let's see how MicSE works. And I will first show how to use the MicSE prover. And in any Linux-like environment, you can download and install MicSE with this command. First, clone the repository and run the make script to build the project. And I will use this program written in Michelson as a running example. And if you don't understand the details of this program, this is a non-trivial program. So if you magnify here, if you look at here, then you can see that the program has an assertion annotated by the command MicSE check. And this assertion is given inside the comment. So the Michelson interpreter will not execute it. And the command MicSE check is provided by MicSE, not by the Michelson interpreter. And for readability, I've put the equivalent Python code here. The last statement performs mutage of subtraction. And our goal here is to prove that no arithmetic on the flow exception occurs at this statement. We can express this safety property by this assertion statement. So the goal of the prover here is to prove that this assertion does always hold during program execution. So once the program and safety property are ready, you can run MicSE with the following command. And let me explain the parameters. There are two required mandatory parameters. First is the program to analyze, and second is the initial storage configuration of the Michelson program. And in this case, this configuration file has these 5 lines. And finally, it takes this is an optional parameter, and in this case, we specify the query to prove. In this case, it is located at line 1 to 6. And you can see a demo video at this URL. So anyway, in a typical laptop, MicSE probably takes about 2 minutes and produces the following analysis report, which shows that MicSE successfully proved the query located at line 1 to 6 of the program, or of the input contract, and which is at line 1 to 6, we have a safety property about arithmetic on the flow from Tezos abstraction. Now, I'll show how to use the MicSE refuter, and let me use the same previous program again, and where you can find another assertion. And in this equivalent Python translation, you can see that we want to prove that the value variable of avail reward calc is always greater than or equal to another variable called given reward. So in this case, this assertion does not always hold. And in the goal of this refuter is to find a buggy transaction sequence that violates this assertion. So again, once you prepare the program and safety property, you can run MicSE refuter with this command. And also, if you're interested, consult this demo video. And in this case, MicSE on a typical laptop will take about 20 seconds and produces this analysis report. And here, you can see that it successfully refuted an assertion at line 344. And here, it provides a bug triggering transaction sequence with concrete parameter values. So with this information, you can actually reproduce the crash, reproduce the bug. Okay, so let me move on to the second part of this talk, techniques behind MicSE. First, let me explain how the MicSE prover works. So the technique behind MicSE prover is the program verification technique. So MicSE prover is based on program verification, and more specifically, it also uses search-based invariant synthesis technique. So let me explain. So this is the standard procedure for program verification. So any program, logic-based program verification takes a program to analyze and a safety property. And it translates the program and the given safety property as a first order formula, typically. And I'll shortly explain how to encode the semantics of P in logic, and the safety property is already given as a logic. So we just put the property with the negation. And this is collectively called verification condition. The program semantics and the safety property to prove are collectively called verification condition, or in short, VC. And then, so this is the first phase of the program verification. Translate the program semantics and property into logic, into a logical formula. And then we use an SMT solver to check its satisfiability, the satisfiability of the VC. And suppose the result of SMT solver is unsatisfiability. Then this means that we have successfully proved the safety of this property because we have negation here. So it is not possible. The unset means that it is not possible to find an input value that negates the safety property, which means that the contract P is safe with respect to this property. And on the other hand, if the prover return the SMT solver returns satisfiability, then this means that it is possible to trigger this negated property, which means that we have found a bug. So in this case, the prover also generates counterexample, which is provided by the SMT solver. So to summarize, the key step of the program verification is to translate the program semantics and property into verification condition. And typically this is expressed in first order logic for safety properties. And then the second step is to check the satisfiability of the verification condition using SMT solver. So this is the outline of the algorithm of the prover. And let me explain some detail using some examples. And for readability, I'll use C-like syntax rather than Michelson, because Michelson is not easy to understand. Michelson is a low-level language, so it is not intuitive. So let's consider this program, this function or method called f, which takes a single argument named a, and there are two local variables x and y. And if a is true, we set x to be 1. So here we assume x and y are also Boolean variables. So 0 means false and 1 means true. And in the second conditional statement, if a is true, we set y to be 1. And at the end of the program, we have an assertion which checks whether x and y have the same value. So to verify this assertion always holds, regardless of the value of the program variable a, we first generate verification condition, which consists of two parts, the program semantics and the negated assertion. So to encode the program semantics, we translate the meaning of the program into, in this case, Boolean logical formula, Boolean formula. So the semantics is, the program semantics is that if a is true, then x is also true. So a and x are true at the same time. Or if a is false, the meaning of the program is that x remains false. So x is false. A and x are false at the same time. And similarly for y, if a is true, y is true. And if a is true, then y is true. And a and y are false at the same time, because if a is false, y remains false. And we put the negation of this assertion at the end of the verification condition. So this Boolean formula encodes the semantics of the program as well as the safety property to prove. So this is the first step of the program verification. And in the second step, we use SMT solver. And in this case, this formula is unsatisfiable, which means that we cannot find a variable assignment that makes this formula true. In other words, for any values of variable a, x, and y, the formula evaluates to false. So in this case, because the result is unset, we have successfully proved that the assertion always holds during the program execution, regardless of the input value. Okay. So the second example, in this example, we have two arguments, two parameters, a and b. And again, they are all Boolean variables. And in the body of the program, we set x to be true if a is true. And we set y to be true if b is true. And at the end of the program, we would like to prove that x and y are equivalent. So again, it is easy to translate the semantics of the program into Boolean formula. If a and x are true at the same time, or a and x are false at the same time, and both b and y are true at the same time, and both b and y can be false. And again, put the assertion, the safety property at the end of the verification condition, and use an SMT solver to check its satisfiability. And in this case, this brilliant formula is satisfiable when A is true and B is false. So in this case, we have refuted this property. So in this case, it is not possible to prove that the assertion does always hold. So this is the basic idea of the program verification. And as always, this is the standard technique, but as always, the challenge in program verification is how to find loop invariant. So in the previous examples, we did not have any loops in the program. But typically, typical programs, and in particular smart contracts, have multiple loops true at the same time. Or if A is false in a single program, I equals J holds before entering the loop, because we have I is 0 and J is 0. So let me to prove all balances. MicSE algorithm consists the prover, the algorithm of the MicSE prover consists of two components: invariant generator and VC validator. So it repeatedly generates candidate invariant, transaction invariant, and rule invariant. And with those rule invariant, the validator first generate the verification condition of the Michelson program, and then check the safety queries. And if it fails to prove the query, the generator produces another candidate invariant, and then generate VC again and check whether the safety query is proved. So this loop is repeated until the safety, the given assertion is proved or times out. So this is the overall algorithm of the first component of MicSE, the prover. And let me move on to the second part, the MicSE refuter. And in this case, the key technique we used is the symbolic execution. So the refuter uses the technique of symbolic execution. And for smart contracts, we have to use the symbolic execution technique with some transaction sequence enumeration. So I'll explain this shortly. So let me briefly explain the basic idea of symbolic execution using this example, C-like program. So we have a function double and a function test me. It takes x and y. And first we double the value of y and name it g. And if g and x have the same value, we again check whether x is greater than y plus 10 and assume in this branch we have a crash. And our goal is to find the value of x and y to trigger this crash. So the symbolic execution works like this. Initially, we set x and y to fresh symbols. And here true means path condition. And true means the path condition, true path condition means that this program point is reachable, trivially reachable for any inputs. And at this point, we double y and assign it to g. So the value of g is this symbolic expression, 2 times beta. And here beta is the value of y, assumed to be the value of y. And again, the path condition is still true. And at this point, the state program, the symbolic state, the value of x, y, and z remain the same as before. But in this case, we have updated the pass condition because we have this the branch condition. So to reach this point, we have to find, we need some values, the values of x and g satisfying this condition, which means that because the value of x is assumed to be alpha and value of g is assumed to be 2 times beta, these two values should be equivalent. So this is the current path condition. And finally, the symbolic executor moves on to this program point, and here we again update the path condition because we have passed through this branch. So following this branch, we assume that the value of x, which is alpha, is greater than the value of y plus 10, and y, the value of y is beta and 10. So this is the current path condition. So at this point, we have this path constraint or path condition. And again, use the SMT solver to find the solution satisfying this condition. And in this case, for example, with x30 and y15, we can make this formula evaluates to true. So this is the satisfying assignment, one of the satisfying assignments in this case. And so this is the basic idea of symbolic execution. And with this actual value, input value, you can reproduce this clash. So the MicSE refuter basically uses this idea of symbolic execution. But in this case, the challenge for smart contracts is that smart contract is a collection of potential methods that can be executed by some external transactions. So we have to run symbolic execution over all possible transaction sequences, over all possible transaction combinations. And it turns out to be a huge search space. So, for example, this is the initial state of the of some smart contract, and it can be. And suppose we have some methods of the contract. So for starting from this initial state, maybe the transaction may call the function bond from, and second, mint token, and approve, and so on. And when you call bond from, we reach this state. And starting from this state, you can again call a function bond from via some transaction, and so on. So there are exponentially many different transaction sequences. And the challenge here is that we have to explore all these possible transaction sequences. This is a very huge space. And assume that only along this particular transaction sequence, we can reach this bug or vulnerability. So the basic idea of MicSE refuter is to exhaustively enumerate all of these transaction sequences and generate VC or run symbolic execution along these sequences and check whether these sequences trigger the crashes or not. And MicSE and we have developed a set of heuristics to prioritize these transaction sequences to effectively explore this huge search space. So this is the intuitive explanation of the refuter. So let me conclude the talk with some performance numbers. So to evaluate the actual performance of MicSE, we have collected a number of Tezos smart contracts from the mainnet. And in particular, we have collected the top 13 smart contracts according to their balance. And these are the addresses of those program smart contracts. and also included in our GitHub repository. And for those 13 smart contracts, MicSE successfully proved or refuted 86%, 87% of the assertions in the program. So this is the number of instructions in each program. And this is the number of queries, assertions in the program, contained in the program. And this column denotes the number of proved assertions, and this column, number of refuted assertions, and here this column, the number of assertions that MicSE cannot prove or disprove. So the failure cases, and this is the time in seconds. So let me summarize. So in this talk, I presented our recent research project, MicSE, which is a tool for verifying and testing Tezos smart contracts. So given a smart contract and a safety property, MicSE consists of two parts, prover and refuter. So we first use prover to prove the absence of bug, safety violation, and if it succeeds, the output is proved. And when the prover fails to prove the safety property, we use the refuter to prove the presence of the bug. So in this case, when it succeeds, we have a concrete error trace to demonstrate the bug. And again, refuter may fail because both prover and refuter cannot be complete. So one lesson from this project is that the standard program verification with some enhancement for Tezos smart contract can be very useful. So as you see the experimental numbers, we could prove or refute most of the queries in the real world Tezos smart contracts. So thank you for your listening. And again, if you are interested, you can find the source code and the benchmark program at this GitHub repository. Okay, thank you.
So thank you, Hakjoo, for the presentation. We are now on to the question part of this very interesting talk. There's quite a few questions already in the chat, but I might start firing one of mine first, and then we'll go on to. There's a lot of them. The first thing is that I would like to know how you had a previous effort on very smart for smart contracts on Ethereum, published in S&P in 2020, right? And how valuable was this effort to implement MicSE? How much did you reuse, and what were the main issues and differences that you saw?
So the question is the difference between MicSE and VerySmart, right? Can you hear me?
Okay. So there are. Oh, so okay. There's another question that comes from the fact that we had some issues here. Could you please try to re-explain, to summarize what you do for loop invariance in the verification?
Okay. Can you hear me?
Yes.
Okay. So the first question is about the loop invariant, right?
Yeah,
because
okay.
Some video issues at the time.
Yes, this is the question.
Okay, so the MicSE has a domain-specific language for expressing invariance, loop invariance. And I think that slide was skipped because of the technical issue of the stream. So we have a language for loop invariant, and we enumerate all possible candidate invariants inside and check whether they can prove the assertions and whether they are inductive invariants. So simple ideas. So we just enumerate all the possible invariant candidates and check each of them whether they will be they are inductive, and at the same time they can prove the given assertion or not. So
Okay, thank you.
Can it be the answer?
Yeah, to me it looks sufficient. I'll try to see if we have more questions regarding that. Okay, so there's another question regarding how much of Michelson you support. Were you able to translate the whole semantics of Michelson or into first order logic, or where there are some constructs that were left out?
Whole semantics of Michelson. Oh yes, we translate. Yes, we translate the whole semantics of Michelson into first order logic. Yeah.
Great. There's a question that is kind of related to that regarding the kind of thing that you can prove regarding the expressiveness of your assertion language. In particular, does it have quantifiers?
No, we do not support the quantified loop invariant because that is one limitation. But yeah, we do not support quantifier, and actually the current invariant language is quite simple. But it supports some arrays, but it does not support quantifier.
Okay. Okay, so there is another question regarding the verification condition that you get. Do they only come from user annotations, or did you generate some of them from Michelson semantics directly?
I don't understand quite precisely the question. So what do you mean by VC come from user annotations, or?
So I guess that the questions, do your conditions, your formulas, are they generated or do they come from user annotated targets, like you can have in Pharmacy, for example, or other, or JML, that kind of stuff?
I see. Actually, the VC generation, I think the both cases are possible. The VC, to generate VC, we consider the user annotation, the assertion statement, and also we consider, of course, consider the Michelson semantics. So we consider every pass from the entry of the smart contract to the target assertion. So encode every possible execution path semantics to generate VC.
Okay, so there's no, the user cannot input specific properties that he can try to verify. He or she can try to verify, right? It's fully automated. Okay. Another tongue-in-cheek question. Which feature in Michelson has annoyed you the most in terms of support or difficulties in implementing?
Actually, according to our experience, developing a verifier for Michelson was much harder than let's say Solidity programs, because Michelson had some kind of first order functions and data structure, that kind of thing. So maybe the first order features of the language. So to support that feature, we developed a very specialized symbolic execution engine that is that supports the symbolic stacks. So that kind of thing was difficult technical matters. Yeah.
Okay. Another question regarding the benchmarks. Someone has noticed that there's an example of MicSE checks in SmartPy. So he or she wonders whether MicSE has support for SmartPy or only works on the Michelson bytecode.
Yeah, indeed, MicSE only supports Michelson. And the SmartPy, the Python files are for just for humans. Yeah, to read the benchmarks. Yeah, the MicSE does not work on the Python code directly. Yeah, only support Michelson.
Great. Regarding security and the refutation, MicSE has refuted some properties in your benchmarks. Did some of them represent potential bugs?
Yes, we think some. Yes, but we think we have found some bugs in Michelson in the mainnet, but we have to more carefully analyze why, how the bugs happen in real scenarios. But currently, we think that we have found some bugs.
Yeah, very interesting. I have some further questions on my own. So in the benchmarks you are presenting, you have some timeouts and things like that, which is expected when you do symbolic execution or verification. Since you rely on SMT solvers for both aspects, I'm curious about the ones you are using, the SMT solvers you are using, and which logics you use with them. Do you use integers, bit vectors, arrays?
We use G3 and we use the integer theory and array theory. Yes, initially we used the bit vector theory, but we somehow changed it to integer to use the integer theory because of the performance problem.
Okay. Okay. There's another question coming from the chat. Did you reuse some code from the Tezos protocol for your code?
Let me think. I remember we used some code related to parsing for Michelson from Tezos protocol, but except for that, we built every other code from scratch. So I do not understand precisely what do you mean by Tezos protocol, but maybe we have the open source parser for Michelson.
Yeah, I guess that's one part of the question. If the question was not satisfactorily answered, please do post a refinement of your question in the chat. Regarding SMT solvers, I have one more. Well, I have many more actually, but you have failed queries. I mean, it's expected. Did you conduct like a postmortem of these queries, why they failed? Any hints at the issues that you encountered?
So can you repeat the question?
Okay, you have failed queries in the SMT queries the formulas that you send to the SMT solvers. Do you have any ideas about why they failed? I mean, it could be due to a number of reasons. It could be the time. It could be due to a lack of refinement on the query. You could pre-process it, use a different SMT solver, or is that just a very hard query and there's nothing to be done about it?
Yes, that's a good question. So when we use this, we only tried the G3 SMT solver, and found that G3 is not so fast in practice, and because of that, we had some performance issues in developing Michelson. And so we have developed some kind of optimization techniques that pre-process the queries. And before sending the formula to G3, we somehow optimize the query using some domain-specific rules for translation to a more efficient query. So that kind of code has been used. That kind of technique has been used in Michelson. And you can find that kind of code in our open source GitHub repository.
Great. Follow-up question then. Do you use more involved program verification techniques like, say, abstract interpretation or very small domains to pre-process these formulas to remove some things that you know how to prove without querying the solver?
I'm not sure. So you mean maybe we can use abstract interpretation or static analysis technique to prune some queries or optimize queries, right?
Mm-hmm.
Yes, that would be possible, but we haven't tried that kind of idea yet.
Okay. New questions coming from the chat. Since you haven't reused any code of the Michelson interpreter, how did you prove that the execution model is actually equivalent to real Michelson? And a question related to that, which version of Michelson protocol, regarding the protocol, did you work with?
Okay, for the first question, so the first question is a concern about the equivalence of our semantics and real semantics, right? Mm. So yes, we do not reuse the Michelson interpreter because the Michelson interpreter is a concrete interpreter, right? But we need some symbolic interpreter, so we couldn't reuse the code. And then the question is how do you prove the equivalence? So actually we didn't prove, but we carefully read the Michelson reference manual and did our best to incorporate the semantics into our symbolic semantics. So yeah, but formal proof, yeah, we didn't try formal proof between our symbolic semantics and concrete semantics. And as for the second question, so which version of Michelson did you try? So maybe this project was started in 2020, June 2020, right? So at that time, we support the latest version of Tezos protocol at the time. So maybe I don't remember the name of the protocol.
Me neither. Someone will post it in the comment section, I guess.
Yeah, but we
might be one of
the latest version at the time.
Okay.
And I found that Python is a growing language. So since then, it has changed some significantly.
Yes.
But we couldn't catch up its evolution.
Understood. Regarding symbolic execution, I have one more question. You talked about using heuristics to guide your search towards a very big search space, which is very usual in symbolic execution. Could you comment on the kind of heuristics that you used? That's the first question. And the second would be, have you tried, if you used many heuristics, have you tried measuring how they impact your search?
So the PES prioritizing heuristic, right? Yes. An important heuristic was we used is that, for example, suppose we selected some function, let's say f, and f defined some variable, let's say x, and then we look for some function g that uses the variable x defined by f. So we use the diffuse relationship of the functions in terms of the local variable, the state variables. So that kind of heuristic was quite effective to prioritize the transaction sequences. And that was the main heuristic we used.
Okay. Do you know how effective that was? I mean, do you have like data showing how it behaved, or your tool, or the tool behaved before and after including this heuristic?
Currently, I do not have concrete numbers, but roughly speaking, it was meaningfully effective. But I don't have. I don't have any.
No. That's fine. Man, this is really hard to come with that kind of data, but in software engineering, you may have this kind of measurement at the ready to select, especially when talking about heuristics, guiding into a big, huge search space. Great. I think we have exhausted our list of questions, if I'm not mistaken. If anyone think I have forgotten something, please post in the comment section right now before we close this seminar. Let's wait a little while. Okay, I don't see anything coming, so I guess that'll be it for today. So thank you once more, Hakjoo, for taking the time first to record the video, and even more responding to the questions, especially at this late hour in Korea. Thank you very much for the effort. Thank you all for attending this Nomadic Labs research seminar. We'll be announcing our next seminars very soon. We don't have, as of yet, fixed closed schedule, so stay tuned for that. In the meantime, stay safe, everyone, and thank you once more for tuning in. And I guess it's goodbye for you. Bye.
Thank you. Bye.
Bye-bye.